Hey guys, today we are doing our last lesson of Chem 20. Yay, we made it. So this one is all about standardization and colorimetry. Standardization is really just more solution stoichiometry. There's nothing about it that's different from any of the solution stoichiometry problems that you've done. And then colorimetry is just a technique that is used to analyze ionic solutions. So we'll go over that quickly today, and then you've got a quiz and a unit test to prepare for, and then after that, just the final exam. Okay, so we're going to be going over standardization first and then colorimetry. These two topics are not really super related. They're just two little things that we throw in at the end here. So for standardization, you do need to know what that means. You need to know what a primary standard is and what makes something a good primary standard. Then we're going to do our calculations based on the standardization process, which, like I said, is just a simple solution stoichiometry problem. And then lastly, we're going to look at different colorimetry techniques. So standardization is the process that is used to find the exact concentration of a solution after you have prepared it. The solution's concentration that is known to a really, really high certainty, like if you're like 100% sure to the nearest like thousandth what a solution's concentration is, then you can call that a standard solution. It has been standardized. A primary standard is a chemical that you can get at a really high purity and that you can measure the mass of really accurately, and then you can use that primary standard to standardize other solutions. So a primary standard, like I said, does have to be completely pure, and most chemicals do contain impurities. It's actually really difficult to find a chemical that is completely free of impurities. So in order for a chemical to be used as a primary standard, it has to not have those impurities as we've talked about before. Those impurities are going to alter your mole ratio slightly because you're going to be accounting for a chemical based on its mass, and yet if there's impurities in there, then the mass of that chemical is actually lower than what you've measured it to be. Your primary standard can also not be a gas because it's too difficult to measure gases and not lose some of them. Your primary standard cannot be anything that vaporizes easily, which just means that it turns into a gas easily. Anything that is reactive with water vapor, oxygen, or other parts of the air can't be primary standards because it's too hard to keep air away from a compound that you're working with. Any substances that are highly absorbent or that can dissolve gases really easily can't be primary standards because they're going to be taking in chemicals and then therefore making themselves impure. Usually soft metals react too easily with the air. They oxidize essentially or rust. So they don't make good primary standards. Sodium hydroxide will absorb water from the air. So there's a lot of common compounds that just don't work well as primary standards. Primary standards include things like zinc powder, sodium chloride, sodium carbonate, potassium bromate, and benzoic acid. Those are all easy to find without any impurities. They're easy to weigh. They're not very reactive. They don't absorb things. They're also cheap, which you want from a primary standard. They're easy to get. They're not toxic. They're not radioactive. So they're safe to deal with, and you can get your hands on them at low cost. So we then use our primary standard to standardize other solutions, which means to find the concentration of other solutions that you have prepared. In order to do that, you do, of course, need to have the mass of your primary standard. You need to be able to determine the moles of your primary standard, and then you're going to be using a mole ratio in order to determine the concentration of the solution you want to standardize. So of course, we're going to need a balanced chemical equation to do that. Then you find the moles of your primary standard using either moles equals mass over molar mass or C equals N over V. Then you mole ratio to the moles of the solution you're trying to standardize, and then go back to C equals N over V to find the concentration of that solution. So this is an example that you guys can look over. But again, all that's happening is C equals N over V, mole ratio back to C equals N over V. So fairly straightforward. Like I said, because this is just a normal solution stoichiometry problem, you guys should be able to do these two questions without me walking you through them. So try those on your own, please. Okay, so for the first question, we have sodium chloride. We've got 14 milliliters of it. It's a 1.8 molar solution. We are reacting that with silver nitrate, 20 milliliters of it, to find its concentration. This is just a simple double displacement reaction, and it's already balanced. So we do C equals N over V to get 0.0252 moles of the sodium chloride, mole ratio to get 0.0252 moles of the silver nitrate, and then back to C equals N over V to get 1.26 moles of the silver nitrate. For the second question, we have our sodium carbonate reacting with nitric acid. It tells us that it produces sodium nitrate, carbon dioxide, and water, and we need to balance this with a 2 in front of our acid and a 2 in front of our sodium nitrate. Then we do C equals N over V, plugging in the concentration and the volume that we know to get 0.024 moles of the sodium carbonate. Then we mole ratio from that to the nitric acid, which is a 1:2 ratio, cross multiply and get 0.048 moles of the nitric acid. And then we plug that into C equals N over V and get 4.8 molar as our concentration of nitric acid. Okay, so that is it for the standardizing solutions part of this lesson. Next, we'll move into colorimetry, which is a method that is used to analyze ionic solutions using color. It usually involves the measurement of light waves that are either emitted, absorbed, and/or transmitted by the ionic solution. And colorimetry works because different ions will appear as different colors. Different ions can absorb and reflect different colors. Sometimes that color can be determined just by the naked eye, but using different technology can make that a lot more precise. So the first type of technology is the spectrophotometer, which is a device that measures the amount of every wavelength of visible light that is absorbed by an ionic solution as the light passes through that solution. And it just measures one wavelength at a time. And it uses that to determine the concentration of different ions that absorb those colors. So the way this works is you have some sort of a light source that's going to be shining through a prism in order to separate the colors of that light source into different wavelengths. You then only allow one wavelength at a time to pass through the solution, and then you have this photocell that can detect how much of that light source actually made it through the solution, and then the rest of it must have gotten absorbed by the solution. So you would just do that again, one wavelength at a time, and then based on how much of each color was absorbed, you can work backwards to figure out what ions were present and in what concentration. Flame tests are much less precise because they don't use any technology like that. Essentially, all you do is you take either like a platinum or a nichrome wire, you dip it into an ionic solution, and then you hold that in a colorless flame. And the flame will then burn different colors based on what that ionic solution was and what ions were present. Ions especially can burn really colorfully, so you can identify them quite clearly based on their flame test. Then there is spectroscopy, which is when you just use a Bunsen burner to do a flame test. Bunsen burners are really useful because they can regulate the flame and because the flame is colorless from a Bunsen burner. We can't do these kind of flame tests at our school because we don't have Bunsen burners, nor do we have any natural gas coming into our school. But back in the old days, they used to have those kind of things in schools. The colored light from the flame test is then passed through a prism in order to separate into the different wavelengths that are present in that colored flame. And then you can, once again, just like with a flame test, kind of work backwards to see what ionic compounds are present. So the only difference between a flame test and spectroscopy is that with a flame test, you just get one color out of it, like magenta or something. Whereas with spectroscopy, you have that magenta flame, but then you separate it into like reds and like a teal or a cyan or something that's present within that magenta flame. So it's a bit more accurate. You can get a bit more information out of spectroscopy where you use the prism than with just the flame test alone. So this is what a flame test would look like. Again, you're just burning that ionic solution to see all of the different colors. With spectroscopy, you then essentially pass that flame or the light from that flame through a prism, and you'll get, this is what you would actually see, is like, you know, a little bit of the different colors that are actually present within that colored flame. And that means that anything that you're not seeing was therefore absorbed. And then the last one is something called atomic absorption spectrophotometer analysis, which is another device that is used to measure light, but this time it's analyzing the light from a flame test. So it essentially takes spectroscopy and then uses technology to make it more accurate. It's similar to the spectrophotometer that we first talked about, in that it uses like actual technology instead of just the naked human eye to measure the amounts of like light that's absorbed. However, with the other spectrophotometer, you are measuring the amount of light that passes through an ionic solution. And this time with the atomic absorption spectrophotometer, you're using the light from a flame test. Okay, that is it. You guys are done all of the lessons for Chem 20. Congratulations. I will see you guys for some review.